So the next speaker is Christian Ott, and he will tell us about core collapse supernova mechanisms.
You hear me? It works. Okay, well, I'd like to thank the organizers for giving me the opportunity to speak. During the lunch break, I recognized that my laptop wasn't working. My keyboard I couldn't type my password. So this talk is really brought to you by Professor Safi Harp, who offered me her laptop to give the talk. So I thank her very much for that. So I want to talk about how supernovae explode, core collapse supernovae, and how we make neutron stars. And I don't claim to have the final answer, but this is sort of what we need to explain, where we need to get to. So we need to go from the progenitor that has some characteristics, mass, radius, composition, angular momentum, magnetic field, to core collapse, which we believe to understand. Then there's some mechanism or some engine that produces either our normal supernova, type 2p, plateau supernova, or standard energy type 1b, 1c supernova. And there must be something that's more extreme that gives us these hypernova explosions, the long gamma ray bursts, maybe no explosion at all, an unnova, a term coined by Chris Kochanik, or maybe a superluminous supernova. And there's characteristics of the progenitor that go into the engine, and they certainly also explain or connect to the explosive signature. So as a supernova theorist, I really have a lot to do. I need to explain the nature of the engines. I need to explain theoretically the flow of explosions and the connection to the progenitor characteristics. We want to understand the energetics, the ejecta masses, the nucleosynthesis, which is very important for chemical evolution. We want to connect to the supernova remnants. We want to understand the geometry of the explosion, the neutron star and black hole kicks, the neutrino, gravitational wave, and photon signatures, and the mass distribution of the compact remnants, the neutron stars, black holes, and we also need to explain pulsars and magnetars. So it's really hard. In this talk, I'm going to focus on just this part, the mechanism and the engine. So here's what we know. You have this evolved massive star, an iron core. The iron core collapses to a protoneutron star. A shock wave is formed. The shock wave stalls because there's accretion of heavy nuclei that are broken up and dissociated. So you have a stalled shock wave. Neutrinos are being emitted from the protoneutron star. And then something miraculous needs to happen that changes the stalled shock into an explosion, and you get your supernova. And you only have about a second or a few to do this. You collapse to a black hole, and there's no explosion or some very weak explosion. Now, to make progress in understanding this, here we understand the physics relatively well. We understand this always happens, but then how to get there or how to get there we don't understand. And it's really a very rich problem. So we need to do computer simulations that solve coupled partially differential equations for magnetohydrodynamics, general relativity, nuclear neutrino physics, and Boltzmann transport of neutrinos, which is a very high-dimensional problem. It's a multi-scale problem where we need to resolve the turbulence surrounding the protoneutron star and inside the protoneutron star, as Martin just said. And we need to, just for the mechanism, we need to include about 10,000 kilometers of the star on our simulation grid. Of course, if we want to connect to the entire star, to the explosive signature, and to the supernova remnant, there are many more orders of magnitude, but I don't even dare to get there yet. And it's fundamentally multidimensional. We know from observations these explosions are not spherically symmetric. So it's 3 plus 1 dimensional, 3 space plus time for the gas dynamics and gravity. And it's 6 plus 1 dimensional, 3 space, 3 phi space, and 1 dimension for time for the neutrinos. But this is sort of the ingredients we want to have in our supernova simulation code. But let's go a little bit back and think about the basic physics of what our supernova mechanism really has to do. And there I want to go back to the Rankine-Hougon shock jump conditions for momentum, where you have the downstream pressure, the downstream ram pressure, the upstream pressure, and the upstream ram pressure. And here's your situation of your stalled shock. This is velocity in units of the speed of light. This is radius. This is a spherically symmetric, a simple supernova simulation you can run on your laptop. Here's the shock wave. It's stalled. Here's supersonic inflow pressing down on this stalled shock. The dynamical pressure, the ram pressure, is much larger than the gas pressure. And here, we're in the downstream situation. The flow is subsonic. The gas pressure is much larger than the ram pressure here. Now, what your supernova mechanism is doing, it's pushing out the shock. And yes, you can see, as you move the shock out a little bit from red to blue to green, your ram pressure will go down because your velocity will be lower. So once you push your shock over some kind of critical point, you run away and you get an explosion. So this is the zeroth order what the supernova mechanism needs to do. It needs to increase this pressure on this side, the downstream pressure, to sufficiently large value to lead to an explosion. So how can we do this? One way is the neutrino mechanism, pioneered already in the 1960s, also with important work here in Russia. Basically, you have a situation here where you have your stalled shock. You have this accretion rate of about a solar mass to a few solar masses per second raining down into the protoneutron star. You get a luminosity from the core down here, which is cooling, and from the accretion. You can absorb about 5 to 10% of these neutrinos in the so-called gain region, where we have net neutrino heating. And this turns out to fail if your simulation is spherically symmetric, so the little simulation on your laptop will not work. But if you allow it to be two-dimensional or three-dimensional, and you get some multidimensional dynamics, you can see this is not spherically symmetric, then you get an explosion. And there's two dynamics that over the past decade, I would say, that have really been identified. And one is the standing accretion shock instability, which is a low mode, sort of L equals 1 kind of instability where you have a sloshing up and down this axis. And the other instability, which turns out, I believe, to be more important, is convection, turbulent convection, with Reynolds number in excess of 10 to the 13. So extremely turbulent in this region where the neutrinos create a buoyant situation where higher temperature gas will bubble up and lower temperature gas, lower entropy gas, I have to say, will bubble down. So let me show you a recent 3D simulation that we carried out, and it's a volume rendering, and I hope the colors will come out right. The bluish and greenish colors are low entropy, and reddish and yellow colors are high entropy. Now, we measure entropy in units of Boltzmann constant per baryon. It turns out this is a really nice scale because it ranges from about 3 to about 30 in the supernova context. So it's a nice scale, and in some sense it's logarithmic because it goes, with ln omega. So let's play this movie. You can see there's a little numerical artifact because we use Cartesian grids, but it becomes spherical. Here's the stalled shock wave, and here's the edge of the protoneutron star. So inside that sphere, the material has not been shocked. This is sort of an entropy of 3 down here, maybe 5, I'm not exactly sure. So over time, neutrinos heat the gas, convection develops. This convection, as I said, is extremely turbulent. This convection pushes out the shock, and you can see it starts developing, and we'll see this in much more beauty in a few seconds. It starts developing protrusions. So there will be hot bubbles that a little bit overshoot, pushing the shock wave out just a little bit more. And over time, the entropy grows, and more gas is captured in this region where it can absorb net energy by the neutrinos. You can see it's pushing out these bubbles, and eventually leading to shock expansion and to a globally asymmetric explosion, which when we saw this simulation made us very happy because finally we're starting to get somewhere where the observers tell us we need to be, namely supernova remnants are not spherically symmetric, and we get non-spherically symmetric explosions. Our colleagues at Garching and Oak Ridge have actually quantitatively shown that they can get neutron star kicks in the few hundred kilometers per second ballpark. So finally we're starting to get some answers of how these explosions occur. So I want to talk a little bit more about why these multidimensional explosions work and spherically symmetric explosions don't work. So here are the effects. So this is a snapshot from a recent simulation I've been running. It's actually a slice through a 3D simulation. And if you're a little fuel parcel entering here, if your simulation was spherically symmetric, the only direction you could move is down and up and down. If your simulation is two-dimensional, you have an additional degree of freedom, the latitudinal direction. And if you're 3D, you have the azimuthal direction as well. So more degrees of freedom means the average time a fluid parcel that enters through the shock that stays in this region of high entropy where it can absorb neutrino energy increases, and the efficiency of the neutrino heating increases. That was an important realization made in the late 1990s, early 2000s. More recently, we realized that there's more. And we just basically went back to Kolmogorov's theory, and we thought about turbulence. And that's something recently by Jeremiah Murphy and by a few people in my group. We looked at the Reynolds stresses that the turbulence is causing. And the interesting thing about the supernova turbulence is that it's anisotropic on large scales. So the Reynolds stress, is sort of the correlation of the velocity variations. The Reynolds stress in the radial direction is twice as large as the Reynolds stress in the theta and phi directions, simply because there's convection, so it's buoyant. So there's more push upward than there's push left and right. And this gives us an effective turbulent pressure that actually helps the explosion. So I want to remind people about Kolmogorov theory. You have the turbulent kinetic energy spectrum that goes with k to the minus 5/3. You have the energy containing range where the kinetic energy cascades down through the inertial range into the dissipation range. In the supernova case, you want to have kinetic energy at large scales where the largest stresses happen. Namely, this up here is where things matter most. Now, turbulence, I said, is anisotropic in the supernova. It is mildly compressible and it's non-stationary. So this is not Kolmogorov turbulence. However, it turns out if you just do simulations, this is again the same kind of plot, now a real plot, not a sketch. This is a Kolmogorov cascade. If you just take the supernova simulation, you increase the resolution sufficiently, it turns out you recover Kolmogorov-like behavior, where at the highest resolution we have a large inertial range that we recover, which was a little bit of a surprise, that supernova turbulence actually behaves like Kolmogorov turbulence, despite the fact that it's anisotropic, compressible, and quasi-stationary only. Now, the resolution dependence here is actually worrisome, because at the lower resolution, this is a logarithmic scale, so you can see there's more kinetic energy on large scales. So it turns out if you run your simulation at low resolution, you end up having typically larger shock radii. So you might artificially help your explosion. So we took a simplified setup and we ran it with the highest resolution we could possibly do using the largest US supercomputer, Blue Waters, up to 150,000 CPUs. And we started out at the standard resolution that typical 3D simulations that solve the full problem can do. And we increased it by a factor of 2, factor of 4, factor of 6. And we just wanted to see when do we actually develop fully developed turbulence. And it turns out we have to go to incredibly high resolution. And I showed this movie just because it's so beautiful, but there's also, of course, science in it. As you can see that as the resolution increases, not only do the turbulent structures get smaller and smaller and finer, there's also greater intermittency. And that's another aspect of turbulence that we ignored or didn't really think about when we were doing our simulations, that at higher resolution you actually get more intermittency, and that can also help because if you are in a critical situation and you have an intermittent growth of large-scale structure, you can get an explosion. But this is sort of the typical simulation that resolution that most of the large-scale, full 3D, full physics simulations can currently afford. So there's a lot of work to do until we have a resolved answer. But let's go on and look at some explosions here. This is a plot that I really like from the Oak Ridge group that did sort of one of the first full 3D simulations with all the bells and whistles and neutrinos and so on. And they have the same progenitor. The red curve here is 1D, so no explosion. This is time, by the way. This is the radius of the shock. Of course, explosion means shock asymptotes to infinity, right? In 2D, they get an earlier explosion than they find in 3D. And that was interesting. And we stretched our heads a little bit. But it actually turns out it's basic turbulence physics, again, that we weren't aware of, because in 2D and 3D, turbulence behaves completely different. In 3D, turbulence kinetic energy goes to small scales, breaks up the plumes, whereas in 2D, you have the ginormous axisymmetric rolls of turbulence, and the cascade goes to large scales rather than small scales. So we now understand why 2D simulations explode more easily than 3D simulations, because in 2D, the kinetic energy goes to large scales, and you end up with large-scale structures that make it easier to explode than in 3D. The problem is nature tends to be 3D, so we need to do these supernova simulations in 3D to get reliable answers. So let me just give you the takeaway on the neutrino mechanism. It does work. We're no longer in a situation where we don't understand how supernovae explode. We can produce these kicks, these asymmetric explosions, but we cannot trust the cheaper 2D simulations. We need to run these very large 3D simulations. One issue that I couldn't go into in detail is that it turns out to be relatively inefficient. It's very difficult actually to reach 10 to the 51 ergs. So we certainly cannot explain a hypernova with this. There's a lot of work ahead. We need better and longer 3D simulations. There needs to be a lot more work of how the progenitor structure connects to the explosion. There's predictions of, we need to make predictions of what happens, of what we will see for the next galactic supernova. And there may be some interesting physics in the neutrino and in the nuclear equation of state sector that has previously been ignored that could actually turn out to be very important. And the Gaussian group has actually done some really nice work on this. So in the remaining 5 minutes I have, I want to talk about magnetorotational explosions. And of course, Martin has already mentioned this a little bit, and I like to show this plot, which really shows you where this energy is coming from. So down here you have angular velocity as a function of radius. This is sort of different stars at the onset of collapse. Then you collapse and you gain about a factor of 1,000 in spin in angular velocity. But that's a factor of million in kinetic energy because it goes with the square. So there's lots of rotational energy, about 10 to the 52 ergs for a protoneutron star that's spinning with the millisecond. So if you just have some efficient way of tapping this energy, there you go, get your hypernova explosion. In addition, and this is actually very important, there's differential rotation here. There's about a factor of 100, no, actually a factor of 1,000 almost, in omega over a radius of a factor of 10 in radius. So d omega dr is very large, which means we have an energy of reservoir of free energy because the lowest energy state is uniform rotation. So if there's some kind of dissipative mechanism, for example, the magnetorotational instability, that can amplify a magnetic field based on that differential rotation. So in order to tap the rotational energy, we need to have magnetic field. Martin just explained to us how we can get the magnetic field. It turns out to get an explosion, you need about magnetar strength magnetic field. Otherwise, this magnetorotational mechanism will not work. And then you drive outflows because then the magnetic pressure actually overwhelms the gas pressure and things start exploding. We can make a millisecond protomagnetar this way, so we can perhaps explain some kinds of gamma ray bursts, maybe some kinds of supernovae, and Sergei will tell us more in a minute. But there is one big problem of this mechanism. It needs very special conditions. It needs very high initial rotation in the core to make that. If you put the angular momentum too far out, it doesn't get to the core in time to give us the protomagnetar that we need to drive the explosion. So this means that this can't explain all supernovae, but perhaps it can explain the 1% or the 0.1% or the 0.01% of extreme supernovae that we want to explain. Again, the problem here is nature is 3D, and if you do the simulation in 2D, you're missing key aspects. Here's the same simulation, everything the same, one where we constrain it to axisymmetry and one where we let it be 3D. So this has very strong magnetic field. It starts launching a jet very early in the evolution, and you get this beautiful structure. Everybody's happy, making this jet. This is subrelativistic, but it will become eventually relativistic. But then if you let the core move and be 3D, it doesn't make a jet. It makes something that I thought my code is broken. But we went and we checked and we understood that the code was not broken but instead there's an instability going on. It's called a well, what is it called? I forget the name. A pinch instability, kink instability, that's what it is. Figured out by Philip Möster and Sherbert Richards, that if you're in a situation, this is well known, again, we had to learn some plasma physics we didn't understand. If you're in a situation where the toroidal field is much stronger than the poloidal field, then this is unstable to that kink instability, and if you think of a foam cord that you press in one direction, it will squeeze it out on the other side, and that's precisely what's happening. There's a little perturbation that increases the magnetic pressure, and it'll just move the field to be spirally and higher order unstable, and it's something that's seen in experiments, and it's a problem in tokamak fusion reactors, and it's also a problem in making jets in a core collapse supernova. So we continued the simulation to later on. We do get an explosion, but it doesn't look like your jet. It looks something like something completely different. The interesting thing is that there is still gas flowing down here onto the protoneutron star. It will eventually make a black hole. So you could have this kind of precursor, strange-looking explosion, but later on you have a black hole that perhaps can drive a relativistic jet. This may just be the early stage. So let me conclude by putting up this slide. We're now able to do these simulations in 3D. There's still a lot of work to do. We have the neutrino mechanism, we have the magnetorotational mechanism. Both work, both are fundamentally 3D. So we've made a lot of progress, but there's still a lot of work ahead, in particular for the young people. Now, this is a very exciting field because, there's Betelgeuse. It might explode. It might have already exploded. And we will get a wealth of observational information from the next galactic supernova. Thank you.
Christian, for the very interesting talk and nice movies. Yes. Questions?
Is it possible to derive the distribution of kick velocities from the simulation of asymmetric core collapse? And can you tell something about the orientation of the kick velocity relative to the spin of a proton-neutron star?
So this hasn't been done fully yet with the 3D simulations, but the Oak Ridge group and the Garshin group have done this extensively on the basis of 2D simulations. So they have basically, they take a star, they run the simulation, and they get a kick. Now, in order to do this statistically meaningful, you have to do this many, many times. So the many, many times is what still has to be done. It's a turbulence system, really. So you push it on one end, something may plop out on the other end, and may behave differently, right? The detailed outcome of this deterministic chaos may depend on a small perturbation somewhere. So you really would have to do some kind of statistically significant set of simulations to get this. So not yet, but hopefully in the near future.
What about orientation of the kick relative to the spin of a proton-neutron star? Are they rather correlated, or the kick is isotropic?
Yeah, so that we don't have any information about yet. Because you can't do this really in 2D, where you would kick it always along the axis of symmetry, which is the rotation axis. You would need to do the 3D simulations, and there's just not enough. The problem is the kick develops over a time of about a second or so. And running one of these simulations for a second takes a year. So, yeah, I'm sorry, we don't have the answer.
Okay, thanks. There was a question there?
I have a question about the very interesting slide about the turbulence spectrum. So I'm wondering, where is the scale of the input for the forcing? And I should think that there should be both the upscale and downscale cascades. It's clear that energy goes to the smaller scales to dissipate, but then you also have extension of the matter. So somehow energy should go to the larger length scales. So could you please comment on this slide?
So in 3D, it has the tendency to go to, statistically, to the small scales. The forcing range here is around the peak. It's around here. And of course, there's some intermittency, And there's some development of large-scale structure. And in fact, in the 3D movie I showed, over time there were these very large regions of very high entropy. And you see it even in this here, where you do develop over time these large regions of high entropy. So there is some development of large-scale structure too, but the trend overall is much weaker than it would be in an axisymmetric simulation that sort of goes directly into that direction. But that's a very good point. And here there's another point I want to make with that. Once you have magnetic field, and once you have a little bit of rotation, there is a natural agent to convert kinetic energy to large scale. And that's something we haven't taken into account.
Okay, let's thank Christian again.